We've all seen it. A tiny crack in a spaceship's window and suddenly, someone is sucked through, their body contorted as they're ejected into space. This dramatic, terrifying moment is a staple of science fiction cinema, designed to evoke primal fear and create high stakes. Movies show a relentless suction with characters desperately clinging on as the vacuum pulls them out. The sound design, roaring winds, high-pitched whistles, amplifies the spectacle. But is this what really happens? Does the vacuum of space act like a cosmic vacuum cleaner? The truth is less dramatic, but far more interesting. It's not about being pulled by space, but pushed by the air inside. To understand what really happens, we need to look at the pressure all around us here on Earth. Let's separate science from fiction and explore what really happens when a spacecraft is breached. Imagine standing at sea level, surrounded by the invisible weight of Earth's atmosphere, even though you can't feel it pressing down on you. Above your head, there's a massive column of air stretching all the way to the edge of space, pressing down with about 14.7 pounds per square inch. That's the same as the pressure inside a car tire but spread across your entire body. You don't notice this pressure because your body is perfectly balanced with the outside world. Your skin, your lungs, and even the fluids in your body are all pushing back with equal force. This balance is what keeps us alive. It lets us breathe easily, keeps gases dissolved in our blood, and prevents our bodies from swelling up or collapsing. Now, picture the International Space Station. Inside, it's carefully pressurized to match Earth's atmosphere, so astronauts can live and work comfortably. But just outside those walls is a near-perfect vacuum, almost no air at all. The ISS is like a giant, high-tech bubble, a fragile pocket of life-sustaining air, held in by strong metal walls and careful engineering. Just like a balloon, the air inside the station is always pushing outward, straining against the hull. The walls have to be strong enough to hold that pressure in, or else the air will escape. If the hull is ever breached, even by a tiny hole, the air isn't sucked out by space. Instead, it's pushed out by the higher pressure inside, rushing to fill the vacuum outside. The bigger the difference in pressure and the larger the hole, the more dramatic and dangerous the rush of air becomes. It can be explosive, violent, and incredibly fast. It's not about some mysterious force in space pulling things out. It's all about the internal force of air molecules pushing to escape, always seeking balance. This principle explains every leak, from a tiny pinprick to a catastrophic hull failure. The pressure inside always wants to equalize with the pressure outside. Understanding this simple but powerful idea is the first step to debunking the myth that space sucks things out. It's all about pressure and how we keep it contained. When people imagine being sucked into space, they often picture a powerful, invisible force yanking astronauts out of their ships. But in reality, sucked into space is a misnomer. The vacuum of space doesn't actually suck at all. There's no mysterious cosmic force pulling you out. Suction, as we know it, is just higher pressure air moving into a lower pressure area. It's not a pulling force, but a pushing one. Air always moves from where there's more of it to where there's less. In the vacuum of space, there stand the kwijger are destansbander dennisonsestans, deribine spans, soundubine spans. No we stand outside air at all, so there's nothing out there to push you or pull you. The only thing that matters is the air trapped inside your spacecraft. When a hole appears in a spacecraft, the pressurized air inside rushes out. Not because space is pulling, but because the air is pushing, desperate to escape into the emptiness. This sudden rush creates a powerful brief wind, a burst of aerodynamic drag that can toss objects and even people around the cabin. Think of it like a dam breaking. When the wall gives way, water isn't sucked out, it's pushed by the pressure behind it. The same principle applies in space. The air inside your ship is like water behind a dam, and a breach is a crack that lets it all escape. The breach is the opening, and the air inside is under pressure, eager to rush out and equalize with the vacuum. The force you feel is from the air behind you, not the vacuum ahead. It's the pressure difference that does all the work. The size of the hole and your position matter. A small puncture might just create a gentle breeze, while a large breach can unleash a violent gale. A tiny hole might only move a few papers or make a faint whistling sound, but a big one can cause a sudden, dangerous decompression, hurling objects and people toward the breach with incredible force. The real danger isn't being sucked into space, but the air we need to survive becoming a hazard in a decompression event. The chaos comes from inside, not outside. So, let's retire the cosmic vacuum cleaner idea once and for all. Space isn't out to suck you up. It's the air inside your ship you need to worry about. The real threat is internal, not external. Understanding this can help us better prepare for emergencies and appreciate the true nature of space hazards. Most breaches in space are tiny leaks, not catastrophic failures. In 2018, the ISS had a 2-millimeter hole in a Soyuz module, barely noticeable. The crew calmly found and plugged it with a finger, then patched it permanently. The force on the astronaut's finger? About the weight of 3/4 of a golf ball. At that rate, it would have taken 18 days to lose all the air, plenty of time to fix it. No dramatic wind, no one being pulled into space. Spacecraft are designed to handle small leaks, with sensors and life support systems providing early warnings. The ISS's air volume acts as a buffer, and minor leaks are technical problems, not instant disasters. The real story is one of engineering and teamwork, not desperate survival. Small leaks are manageable, not cinematic. The danger is real, but rarely as urgent as movies suggest. Calm, methodical action is the norm, not panic. But what if the breach is large, a window blows out or an airlock fails? Now we have rapid, even explosive, decompression. The air rushes out in less than a second, creating a violent, brief windstorm. Everything not bolted down, tools, equipment, people, can be hurled by this force. The main danger is not being pulled through the hole, but the explosive shove of the escaping air. The pressure drop can cause fatal lung trauma, and the wind can knock you off your feet. But this event is over, almost instantly. Once the air is gone, the force disappears. The real threat is the initial blast, not a drawn-out struggle. Afterward, the dangers are lack of oxygen, cold, and exposure to vacuum. Imagine you're inside a spacecraft, and suddenly, there's a breach, a hole opens up, and air starts rushing out. What if you're right in the path of the escaping air? This is a scenario astronauts train for, but the reality is even more intense than most people realize. The force you'd feel depends on two main things: your position relative to the breach and the size of the opening itself. A small puncture might create a strong gust, but a large hole can unleash a torrent of air, turning the situation from dangerous to catastrophic in seconds. If you're some distance away from the breach, the force is like being shoved by a large adult, enough to knock you off your feet, but if you manage to grab onto something sturdy, you might be able to hold your ground. The key is to react quickly and brace yourself, but if you're unlucky enough to be blocking a large opening, the force can skyrocket to thousands of newtons, far beyond what any human could resist. In that moment, you're completely at the mercy of the escaping air. You'd be ejected instantly, like a cork from a bottle under pressure. The air doesn't just push, it blasts you out with incredible speed, leaving you no time to react. This is one of the rare times when reality actually matches the drama of a movie scene. The suddenness and violence of the ejection are very real, but unlike what you might see in films, you're not squeezed through a tiny hole. Instead, you're blasted out in an instant, propelled by the force of the escaping air. It's important to remember, the force is always a push from behind, created by the air pressure inside the spacecraft. Space itself isn't pulling you out, it's the air inside that's doing all the work. Once you're outside, there's no mysterious force dragging you further into space. You simply drift, carried by your own momentum, surrounded by silence and emptiness. The real danger comes from being in the wrong place at the wrong time, caught off guard by a sudden breach, with little time to react. If you're on the floor, or tucked away from the direct path of the airflow, you're much less likely to be ejected. Staying low and out of the line of fire can make all the difference. The greatest risk is for those standing directly in front of a large breach, where the full force of the escaping air is unleashed. In space, even a split-second decision can mean the difference between safety and disaster. The real killer in a decompression event isn't the vacuum, it's the air and everything it carries. As air rushes out, loose objects become deadly projectiles. A simple tool can become lethal, accelerated by the escaping air. The ISS is filled with thousands of items. In a rapid decompression, it becomes a storm of shrapnel. The risk of being hit by debris is often greater than being ejected. The bigger the breach, the more violent the storm. People and objects can be hurled out in a fraction of a second. The Hollywood vision of a lone astronaut fighting the void misses the point. The real dangers are explosive air, flying debris, and then, only then, the risk of being pushed out. Surviving the initial blast inside is the first challenge. In those first moments, the most dangerous place is inside the ship, not outside.